Hey folks, we're going to start our year with a little introduction to computer history. So the first question, what is a computer? Well, today of course we know computers as laptops or desktops. They connect to the internet, but originally computers were people. So the term computer actually meant one who computes, a person who does math essentially. And this person, much like a computer today, had to follow a very strict set of rules. They could not deviate from them. And so the beauty of a human computer or a modern computer is when you have an input, your output is always the same. So if you are doing a mathematical table, 3 times 3 is always 9. It can't be anything else. There's no rule to change that. And so that was sort of the introduction of computers is as a person who would do these computations. So here you see some human computers back around the probably World War I, World War II era. And one thing I want to point out here, notice that these computers are almost all women. And there's a good reason for that. What has driven computing a lot has been war. That's one of the big things. And when war drives technology, it has some other consequences. With World War II, with Vietnam, there were drafts, and all the men went to war. The women were not drafted. And so the women had to fill in all these spaces that were now in the workforce. So you might remember that Rosie the Riveter poster. So Rosie was building airplanes now, thing that would have normally been a man's job, but since the men have all gone to war, now the women have to step in and do that job. And so traditionally, human computers were more often women. So here you see again, about the time we were building the atomic bomb, we required a lot of women computers as well. What we often consider the father of the modern computer is the ENIAC, and the ENIAC was programmed primarily by women for that very same reason. And so you can see some of the names of those first computer programmers right here. And then here we have a photo of the ENIAC, and you can see also there's a woman reading a program there in the background. So we'll come back to the ENIAC. This is a pretty important piece of history here. Now, after we get done with computers being the people who do the computation, they eventually have to become machines. And so the first computer machine was a mechanical machine. The Babbage engine is the most famous of these. So here's the Babbage engine. This was designed by Charles Babbage. This would have been, I believe, the late 1800s. And the way this worked is you would program your initial settings in by turning some wheels at the top here. And then you see that crank handle on the right. As you turn that handle, every time you make a revolution, which I think is 2 turns of the handle, it would cause this cascading effect of gears and cams to change. And as they did, computations would happen. And this is a pretty neat device. It would actually print a tape with the mathematical tables on it, and then it would also make an imprinted table so that you could print copies of that later, and it would do that in wax. There will be a video about the Babbage engine that I'd like you to watch right here, so I'll link to that later on. Now, after these mechanical computers, what's interesting actually is that Charles Babbage never actually built what you just saw there. This mechanical computer was built later on by someone who wanted to see if it would work. Now, Babbage designed it, he had it all on paper, but he never had that proof of concept. And so it wasn't until basically 100 years later, somebody actually decided, we should build this thing and see if it works like Babbage thought it did. And sure enough, it did. So after we get done with the mechanical side of computers, now we start to power them with electricity. And when we get to electronic computers, this is now approaching more what we think of as a real computer. So in order to do that, we have to be able to send electricity one direction or another. This is how we make logic gates. So ands and ors and things like that. Perhaps you've heard those terms in computing. And in order to do that, we do that multiple times, right? If you had a tree and you wanted to get to the far left side, the far right side, you would work your way down the tree or up the branches perhaps, right? Every time you hit a branch, you need another decision to be made. And the way we would do that in early electronic computers was with a vacuum tube. So here's a vacuum tube. A vacuum tube could either pass electricity or not pass electricity. And you string enough of those together and you can start doing things in binary, zeros and ones, right? A 1 is passing electricity, a 0 is not. And so again, we're back to the ENIAC, the EDVAC, some old computers like that. And these were programmed with originally cables. You can see all of these cables through here. And if you wanted to write a new program, rather than sitting down and writing code, you would replace all of these wires and put them in a different order. And that's how these were initially programmed. Later on, we could program with punch cards. So we have literally a card and you punch out certain numbers, certain areas, and then you feed that card into the computer. And that was your input instead. Now, the vacuum tubes were slow. They ate up a lot of electricity. Because of that, they produced a lot of heat. I mean, look at the size of these things. This you can still buy vacuum tubes today, and they'll be maybe this big, maybe a couple inches tall. You'll find them in some amplifiers, especially higher-end guitar amplifiers, but we don't really use them for logic anymore because these would waste a lot of heat. Think about an old incandescent light bulb compared to an LED bulb of today. The old light bulb might be 100 watts and the new one might be 7 or 8 watts. The old one would produce so much heat that you couldn't touch it while it was on. If you had to change that light bulb, it would need to be out for some amount of time before you could actually touch it to unscrew it. An LED bulb, you can just go up and touch. They're safe, they're cool. That's kind of where we are with these vacuum tubes. They produce a lot of heat, they're wasteful. They were also not very robust. They would go out and have to be replaced pretty frequently. Brings us actually to an interesting piece of trivia. You've probably heard of debugging a program where there's a bug in the code. This is where that comes from. The original bug was actually a moth that would fly in. Moths are attracted to the light and the heat of these vacuum tubes. The moth would fly in, flap around, get trapped, and short circuit the vacuum tube, which would cause the tube to have to be replaced. But before it could, you had to literally debug the machine. You had to remove the moth. So that's where that old debugging term comes from. So when we move away from vacuum tubes, we go to something that can do the same job where it can either pass electricity or not, but now we have the transistor. The beauty of the transistor is that it is solid state. It's much smaller. You can see here in the upper left-hand corner, this was the first transistor, and it's large. I mean, we're still looking at something, you know, this big. But nowadays, if you look at the bottom, you've probably seen transistors like this on modern electronics. They're tiny. This is, you know, a quarter of an inch tall, perhaps. And we can make them even smaller. Here is a microscopic transistor. You could not see this with the naked eye. So transistors gave us the same thing that vacuum tubes did, but they did it more efficiently. They used less electricity, they produced less heat, and because of that, they could run faster. The heat really kicks in when you switch from a 0 to a 1 or a 1 to a 0. So anytime you move back and forth, you generate heat. With an old vacuum tube, moving back and forth, you know, if you did that 100 times per second, you would generate a certain amount of heat. Well, a microscopic transistor could do that tens of thousands or millions or tens of millions of times per second and produce less heat, and therefore it's faster. And eventually we get to integrated circuits. That's our next step. So integrated circuits simply takes multiple transistors and puts them together in a single location. This is where we get the chip. So you can see in the upper left, there's your first integrated circuit. They took a couple of transistors and soldered them together. A modern chip, like the bottom right there, is still around, still on electronics, still in computers. The 555 might be one you've run across. It's a timer chip. It's very famous. You'll find those in all sorts of electronics projects. Now, while this looks like a processor, it's not a processor yet. An integrated circuit like this still only performs certain jobs. It's not generic yet. We have to get to the proper CPU or central processing unit before we make these chips generic. So a CPU has a big instruction set. You can write code that tells it to do certain things, whereas with a regular old integrated circuit, they can only perform a certain number of functions. So this is where we've genericized that. So you can see the Intel's 4004 there. It looks just like those integrated circuits that we saw earlier. But that was the first general purpose CPU. It's programmable, it's reprogrammable. And then down at the bottom we have an 8th gen Core i7. So, you know, sort of a modern-ish CPU. And look how far we've come. Those are not terribly different in size, but we go from, what have we got, maybe 16 pins to hundreds of pins. We go from a very small instruction set to a huge instruction set. So while this represents the first and then the modern processor, they're really very little alike. So overall, what trends have we seen as we progress from humans to mechanical to vacuum tubes to transistors, integrated circuits, and finally CPUs? What do we see there? We've seen computers become smaller. This doesn't really apply to the humans portion, but the mechanical computer that Babbage designed was very large. It was, twice the size of the desk I'm sitting at. Now, when we go to the ENIAC, actually, it takes up a whole room. So the first electronic computers were room-sized. They required entire power stations to run them. They required several people to manage them, and still, they had less functionality than a modern day 4-function calculator that you can go into the dollar store and purchase for $1. But we had to start somewhere. So computers have become smaller. When we go from vacuum tubes to transistors, the whole package became smaller. Transistors to integrated circuits, the whole package became smaller. They've also become faster. The ENIAC was capable of performing, maybe thousands of operations per second, whereas when we get to the transistor, we're at tens of thousands, hundreds of thousands. And of course, now we're in the gigahertz range with modern processors. So gigahertz, we're talking billions of operations per second. A 3 gigahertz processor can do 3 billion things every second. That's a far cry from the ENIAC's few thousand. They consume less energy, and this is a trend we've seen peak a couple of times. From the ENIAC, where it required huge amounts of electricity, eventually we become, instead of room-sized, we become cabinet-sized, and now computers can be purchased not just by governments, but by large businesses. And then we go from cabinet size to sitting on a desk, and now individuals can afford to own them. From there, we even go to laptops. We go to portability. Laptops into modern smartphones. The modern smartphone has the same capabilities that a computer had just a few years ago, and now we can stick it in our pocket. So overall, they've become smaller, and because of that, they consume less energy. The ENIAC from a vacuum tube to a transistor, we're talking orders of magnitude in energy savings. So a transistor, with a vacuum tube, you could never have had a computer powered by battery. You could never have had a laptop with a transistor, integrated circuit, that sort of thing. Now you can get to where you can power it on the go. Computers now generate less heat, and this is ultimately why they are faster. And this is an interesting concept to wrap your head around. If you think about a modern computer with a regular, let's say, Intel Core i7 CPU, maybe you've seen computers that have water cooling on them. Why does water cooling make a difference? Well, it can get heat away from the chip faster than a regular fan can. So if we get the heat away, we can overclock the processor. So a processor that is designed to go at 3 gigahertz, maybe we can make it go 3.2, 3.5, maybe even higher, 4 gigahertz. And we're now doing more work in a given amount of time. And the whole reason we can do that is because we are getting the heat away from the chip. So as things become smaller and more energy efficient, they naturally produce less heat. That's the entropy that you learned about in science class. Anytime energy changes from one form to another, some is lost as waste heat. The more efficient we can make them, the less heat they generate, then the faster we can push them. So the whole reason that chips have gotten faster is because they produce less heat. And now the other big concept here is we have changed how we interface with computers. So with the ENIAC, we plugged cables in, and then later on we started to put punch cards in. And eventually we got to the point where we're using keyboards, and then keyboards added a mouse. And now we have sort of a modern desktop computer, keyboards and mouse. But think about a smartphone. We don't really use keyboards and mice with smartphones. We use touch sensors, touch screen. We have fingerprint readers. We talk to them now with voice recognition. So the way that we interface with the computer, input and output, has changed a lot. The output of these devices might have been printed tape. And then we discovered that we could put it on a monitor. So we went to text-based monitors, and then graphics with colors. Well, now the computer can speak to you, or maybe your Echo device talks to you. So the input and output has changed over the course of the years. we also use computers for different things and in new ways. So the ENIAC was designed to do some basic math. Computers around the World War II era were to break codes. So these were things built specifically to help with war. We want to say, can we build a better bomb? Can we break code and protect ourselves? We weren't playing games on them. We weren't watching movies on them. So that has changed. It wasn't until the personal computer came around that we started to play games. And games went from 2D games to 3D games to VR games. When I first started using computers in the 80s and 90s, we didn't watch movies. They weren't capable of playing video. So the idea that we could watch a movie on a computer would have been foreign, as little as 25, 30 years ago. The internet didn't exist at that point either. And so the fact that we now have access to the multitudes of information available on the internet is something that, again, would have been foreign not that long ago. So the big takeaways here are that computers have progressed in a manner that has been consistent, right? Even when we change from one new technology, vacuum tube to transistor was a monumental moment. Transistors to integrated circuits, a monumental moment. But despite that, they have done the same things. They've always become smaller, faster, more energy efficient, and producing less heat, which is what allows them ultimately to become faster. So that has not changed despite these big jumps. The way we interface with computers has changed in the past, will change in the future. The things that we use computers for has changed in the past, and again, will change in the future. So this is what I'd like you to think about. Based on how computers have changed in the past, what do you think the computer of tomorrow will look like? And not literally tomorrow, but what will a computer look like in 5 years? Will it be terribly different? Maybe not. But what about 20 or 40? What will a computer in 50 years look like? I've been using computers. I built my first computer when I was 17, I think. And the computer that I built today would be built in a similar way. I'd put components in a case and it would have a motherboard, but the things that I would use it for would be different. The way it would look much different. So what will a computer in 20 or 50 years look like? How will we interact with them? I had a keyboard and mouse on my first real computer. I had to upgrade it to get speakers. So it didn't produce sound until I added a sound card to it. So in 20 or 50 years, how will we give input to a computer? How will we communicate with the computer? How will it communicate back with us? Will it still be a monitor? Will it be something totally new? Also think about what activities we might use a computer for in the future. So if I roll back to my childhood, I could not have imagined that we watch movies on them, and now that's the only place I watch movies. So in 50 years, what will we do with computers that we don't do with them today? So those are the big questions I want you to think about. So that is our little introduction to computer history. I'll have some links and some videos for you as well. Thanks for watching.